Hello, and welcome to the last part of my lecture series on stability. In this part, I present some recent results concerning the stability of compact minimal submanifolds in the Berger sphere. So the talk is divided in three parts. In the first one, I will present what a Berger sphere is and its properties. In the second part, I will show examples of minimal submanifolds in the Berger spheres, and after that I will present the main results. And this is a joint work with Francisco Urbano. Okay, what is a Berger sphere? So a Berger sphere is nothing but a round sphere endowed with a metric that deforms the standard metric in the direction of the Hopf fiber. Analytically, the metric, which is going to be denoted by angle brackets, is given by the standard metric G on the spheres plus a term that depends on the parameter tau that we are going to call the parameter of the metric, and the standard metric in the direction of the tangent part of the Hopf fibers. So the vector field psi, which is tangent to the Hopf fibers, is a unit Killing field, and we are going to call vertical whatever is collinear to psi, and horizontal everything that it's every vector field that is orthogonal to psi. The Hopf projection of the odd-dimensional sphere with this metric into CPN is a Riemannian submerger for all tau, whose fibers are vertical geodesics tangent to psi of length 2 pi tau. Here we see the precise geometric meaning of the parameter tau. Tau is increasing or decreasing the length of the Hopf fibers. The isometry group is those matrices in the orthogonal group that commutes or anti-commutes with the complex structure of the complex space. Moreover, the Berger sphere are homogeneous manifolds. Its Ricci and sectional curvature are bigger or equal than 0. In this case, we are going only to consider the parameter. We are restringe ourselves to parameters less or equal than 1. That is, we are going to consider only Berger metric that decreases the length of the Hopf fibers. And finally, the injectivity radius of these manifolds is just tau times pi in all the points. Okay, just to try to get a picture of what a Hopf fibration is, I'm going to present here these beautiful pictures by Niels Johnson, where we can see the three spheres stereographically projected to R3 and then R3 compressed into a ball. And on the right hand side, for each point in the two sphere, we see in the left hand side the corresponding fiber with the same color. Hence, for instance, if we consider a parallel in the two sphere on the right, then we get a Hopf torus on the left. The picture is to see better what is happening. The picture of the torus is not complete. These manifolds were introduced by Marcel Berger in '62, and they provide counterexamples to extensions of several results. I will mention some of them. So first, at the end of the 50s, Klingenberg shows that for a compact even-dimensional manifold, the length of a closed geodesic is always less, so is always bigger or equal than 2 pi over the square root of k if the curvature is positive and bounded above by this constant k. If M has odd dimension, then we've got the same inequality, but in these times only if the curvature of the ambient manifold is pinching between 1/4 of k and k. Well, there are examples of Berger spheres with curvature lines lying in this pinching for delta between 0 and 1/9, and with closed geodesics of length less than 2 pi over square root of k. So in the odd dimensional case, we can now get a general result, like in the even dimensional case. Okay. Next, I'm going to mention the result by Hertz in the 70s, that for any metric on the two sphere, the quantity λ1 times area is bounded above by 8 pi, and the equality holds infant only if h is a constant curvature metric. Okay, so Berger posed the following question, which is actually generalize the previous inequality to higher dimension. So if I consider a compact manifold M, does there exist a constant k depending on M such that the first eigenvalue of the Laplacian satisfy this inequality? The answer is no. The question is false. And Tano showed that of dimensional spheres, Berger spheres, show that this is not possible. And the way he showed this was computing the spectrum of the Laplacian of the Berger metric, which will be important for us in this talk. Well, next, the Berger sphere are the first non-trivial example of a collapse. The limit of this collapse in dimension 3 is S2 with a metric of constant curvature 4. If we think on the Berger metrics of lowest dimension, which is dimension 3, and we take the parameter tau tends to 0, then the length of the Hopf fibers goes to 0. That is, each Hopf fiber collapses to a point, and then the three manifold collapse to S2. They also appear naturally at geodesic distant spheres in the complex projective space. Again, here we are assuming that tau is less than 1. In the tau bigger than 1 case, they are actually geodesic spheres, but in the complex hyperbolic space. Okay? Throughout the talk, we only deal with the case tau less than 1, because the case tau bigger than 1 is of different nature. Okay, in these settings, the restriction of the complex structure of the Euclidean complex space and the complex projective space to the Berger sphere are the same. And the normal vector field to the Berger sphere in CPN plus 1 is actually just the J psi. I mean, psi was the killing field tangent to the Hopf fibers. So if we take its rotation with respect to complex structure of CPN, we actually get the normal vector field of the Berger sphere in the complex projective space. Okay, so now we have presented the manifold in which we are going to study the stable compact minimal submanifolds. First, we need to know which kind of minimal submanifolds do we have. Okay, so first we start studying the most simplest one, which are the totally geodesic. Okay, so if I take a totally geodesic immersion, then it is congruent either to a Berger sphere inside the Berger sphere, I mean a low-dimensional Berger sphere inside of it, which is given in this way, or a totally real submanifold, which is just taking the dimensional sphere and considering immersed in the Berger sphere as taking each of the coordinates as a real coordinate. Or we have as a limit case, the dimension is 1 and the immersion is actually a geodesic, which has more kind of that the one showed in 1 and 2. Okay, so these are the most simplest one, the totally geodesic. I would like to remark that in the first case, the killing field psi is tangent to the submanifold, while in the second case is normal. So in this sense, the most simple samples are well behaved with respect to the killing field. Okay, so next I'm going to present a construction to produce more examples. So if I start with a complex immersion in CPN given by the immersion psi, then I can construct it what is called the S1 bundle over N compatible with Hopf fibration, which is an immersion phi which is defined in a odd-dimensional manifold M into the Berger sphere that commutes with the diagram that is shown in the frame, in the slide. Okay? Well, we can also consider which is what is called the induced S1 bundle by the Hopf fibration, which is also an odd-dimensional manifold M and an immersion over the Berger sphere that commutes with the diagram. And the relation between the S1 bundle and the induced S1 bundle is that the first one is always a covering of the second one, and finite coverings, and the order of the covering is going to be the order of phi. Okay. So these S1 bundles are always minimal for any tau. Okay. And we are going to call it throughout this talk just Hopf bundle for short. The killing field is always tangent to the immersion phi, and the normal phi is invariant on the complex structure J of the complex projective space. Remember that we can put our Berger sphere in the complex projective space as a distant sphere. And what will be important later in the talk is that properties 1 and 2 characterize a minimal inversion as a Hopf bundle. Okay, so whenever we've got a minimal inversion which is minimal for any tau and which psi is tangent, then it has to be one of these Hopf bundles. Okay, so now we are going to present the simplest examples of Hopf bundles. The first one is the totally geodesic Berger sphere, which is actually the induced bundle by the Hopf fibration over the complex embedding of CPM in CPN, okay, which is written down in the slide. If in the case M0, so we are dealing with the S1, we've got the following situation. So S1 is the induced bundle, but since S1 have finite coverings by itself, we can consider Hopf bundles of any order S, just considering or taking the map that maps the complex number set to the power of S. Okay. The other examples that we are going to see is the Veronese examples. So let phi be the immersion from the 3 sphere with this particular metric to the 5-dimensional Berger sphere, given in complex coordinates by that expression. Okay, so we can see that this is actually a Hopf bundle over CP1, taking as psi. I'm looking into the diagram in the bottom part of the diagram, Tuki and psi, the well-known Veronese embedding. Okay. So now we can consider the induced bundle. In this case, the induced bundle, the induced Hopf bundle is given by RP3. So the Veronese example is actually a Hopf bundle of order 2. Okay, so the main topic of this talk is to study the stability of compact minimal immersion in the Berger sphere. So let's first write down how is the Jacobi operator. So the Jacobi operator has this long form. The first two terms are just the normal Laplacian and the term involving or concerning the second fundamental form of the immersion, and the third term is the term coming from the curvature of the Berger sphere. Here I have highlighted two terms in red. The first one is the normal component of the psi, the Killing vector field psi, and the second one is related with the behavior of the normal bundle with respect to the complex immersion J, complex structure J, sorry. So if our immersion is well behaved with respect to psi and J at the same time, then our Jacobi operator will have a simple form. Okay. If in the case of oriental or hypersurface, then as we have seen in part 2 of this lecture series, the Jacobi operator L becomes in a Schrödinger operator given in the slide as the Laplacian plus the length of the second fundamental form plus a term involving the Ricci curvature of the ambient manifold, which in this case is controlled by the dimension of the Berger sphere, the parameter tau of the Berger metric, and also it appears the angle function, which is just the scalar product of psi and the normal vector field to the immersion. Okay. Directly from this expression, we have the following proposition that every orientable compact minimal hypersurface is always unstable, and the first eigenvalue of the Jacobi operator in this case is always less or equal than -2n tau squared. The proof is rather easy, and it is just considering as test function the constant function 1. Okay. Okay, so now we are going to see what can we say about the index or compute the index of the totally geodesic Berger spheres. So in this case, we have this result that says that the index of a totally geodesic Berger sphere of dimension 2n plus 1 is 0 if the parameter of the metric is less or equal than some special value that depends on the dimension of the submanifold, or twice the codimension if the codimension if the parameter tau is above this value. Again, I am restricting myself to values of tau less or equal than 1. Moreover, if n is 0, I mean we are considering a circle, a closed geodesic, then and phi is one of these coverings of order S, then this covering is stable if and only if tau squared is less or equal than 1 over 2s. I would like to highlight that these two special values for which the index is 0, that is, our immersion is stable. This is something that do not happen in the standard sphere. In the standard sphere, every compact minimal submanifold is always unstable. Here, we have seen that for the if we make the length of the host fiber short enough, some stable submanifolds will appear. So this special value is 1 over the dimension of the submanifold plus 1, and in the case of the covering of the order S is precisely 1 over S, the order of the covering, times the dimension plus 1. Okay? The main ideas to compute the index of the totally geodesic Berger sphere are the following. First, the normal bundle has a global orthonormal reference, which is these pairs of AJ and IAJ, I being the complex number in Cn plus 1. Second, the Jacobi operator is just a translation of the orthogonal Laplacian and can be decomposed in m minus m equivalent operator L, okay, acting on section of the forms f aj plus j I aj. I mean, I consider I decompose the normal bundle in subbundle of dimension 2 generated by A and IA with IA fixed vector field in the complex plane, complex space, and this operator else acts like in the expression in the slides. Okay, it's not so complicated expression, but it involves the grading of the functions. Okay. Finally, the spectrum of the Laplacian for the Berger sphere is known. That is the result of Tano I previously mentioned in the talk. And putting together all this information is then not so difficult to actually get the eigenvalues of the Jacobi operator and count how many of them are negative, and so getting the index. It is also possible to also compute the nullity of the totally geodesic Berger spheres. Okay, the second proposition is the computation of the index of the Veronese example. And in this case, we again see that the index of the Veronese examples is 0 for tau squared small enough, and then is increasing to 6 and then to 8 until we arrive to the round sphere, which corresponds to the value tau equals 1. If we consider the 2 covering of the 3 sphere over RP3, then we see that in this case is stable if tau squared is less or equal than 1/8, is for a smaller value of tau squared, and then goes increasing until we arrive at the the standard spheres that correspond to tau equals 1. I would like to highlight again that the value for which the Veronese embedding of RP3 is stable is for tau squared less or equal than 1 over dimension plus 1. And in the case of the order 2 covering is 1 over 2, the order of the covering, dimension plus 1. So in both examples, this value 1 over dimension plus 1 or 1 over the order of the covering times dimension plus 1 plays an important role. Okay, now I am going to present the main results of the talk. So I have presented a huge family of minimal examples in the Berger sphere for any tau that are the Hopf bundles, and those examples are well behaved with respect to the killing field psi. So a natural question arises: are they stable in the Berger sphere? We have seen that 2 of these examples, which are the totally geodesic Berger sphere and the Veronese examples, are actually stable if the parameter tau is less or equal than some special value. Okay, so these examples suggest that the stability of Hopf bundles will depend on the dimension of the Hopf bundle, the value tau of the parameter of the metric, and the order of the bundle. Okay, so the first main result is the following: if I consider an immersion of a Hopf bundle of order S over a complex immersion, then if the parameter tau square is between 0 and 1 over S dimension plus 1, then our immersion is stable. That is, we get the best possible result in this case, seeing we have already shown that spheres and Veronese example are unstable beyond this special value. Okay. In the case the order is 1, I mean we are dealing with the induced Hopf bundle, then phi is stable if and only if tau squared is less or equal than 1 over dimension plus 1. So the main ideas or the proof are the following. First, we consider our Hopf bundle inside the Berger sphere and the Berger sphere inside CP n+1. Okay? By the properties of the Hopf bundle, the tangent bundle to the our submanifold M can be decomposed as the part collinear with psi and the orthogonal part, which I'm going to call D. And the complex structure of CP n+1 leaves invariant both this subbundle D and also the normal bundle. Okay, now we can, the first step is to rewrite the quadratic form Q over a normal section eta using the operator D. D just measure how far our normal vector field how far is from the holomorphic with respect to the complex structure J induced in the tangent distribution D. Okay, then we can express the integral of Q in terms of the standard metric. Since both Berger metric and the standard one are related by the parameter tau, we can actually write down everything in the standard metric and decompose any normal section in sum of agent section of the vertical normal Laplacian. Okay, and finally getting a lower bound of the index metric by 0 using our hypothesis that the parameter tau square is less or equal than 1 over the order of the Hopf bundle times the dimension +1. And then we get that these examples are stable. Okay, so I recall that in the standard sphere there are no stable compact minimal submanifolds. This is the classic results by Simons in the 60s. So then any compact minimal submanifold Berger sphere for tau, for the parameter tau next to 1, should also be unstable. Think that for tau 1 we are actually in the wrong sphere. So if tau is next to 1, we just make a slightly deformation of the standard metric on the sphere. So it is reasonable to think that since in the standard sphere there is no stable compact minimal submanifold, for tau for metric next to that one, there will also be no stable compact minimal submanifolds. So some question arises. What is the first Berger sphere, that is the biggest value of the parameter tau, for which admits compact stable submanifolds? We do know that there are value tau for which there are compact stable minimal submanifolds. So the question is, what is the biggest value for this to happen? And the second question is it possible to classify the compact minimal stable submanifolds for this particular Berger sphere, for the one with the biggest parameter tau? We are going to answer both questions. The first one is that this biggest parameter tau is actually 1 over dimension +1, which is the first value of tau square for which the Hopf bundles are stable. And the answer of the question 2 is that the only compact minimal stable submanifolds for that particular parameter are the stable Hopf bundles. Some remarks will be in place in the answer of this second question. Okay, so the first question is answered by the following theorem, which says that if we consider a minimal immersion of a compact D manifold, and we assume that tau square is bigger or equal than 1 over dimension +1 and less or equal than 1, and our immersion is stable, then tau square must be this special value, the dimension of the manifold must be odd, and phi is actually a Hopf bundle of a complex submanifold CPM. Okay. As a corollary, if we consider a minimal embedding, now we assuming further that our phi is an embedding of a compact manifold, and again tau square is between the special value on 1, R1, and our immersion is stable, then this happens only if tau is the special value 1 over dimension plus 1, the dimension is odd, and M is actually the induced Hopf bundle over a complex submanifold. Okay, so in this sense, we are characterizing completely the compact stable minimal embeddings in this in this range of parameter of the Berger matrix. Okay, so the remarks are the following. We do not know if Hopf bundles are stable for that special value of the parameter. Okay, we do know that if in the case of the induced bundle, in the case of order 1, that is the case. But if the order S is bigger than 1, we only know that they are stable if tau square is less or equal than 1 over the order S times dimension plus 1. So we conjecture that the Hopf bundles are actually unstable for that particular value of the parameter. So actually in the previous theorem, in the previous corollary, we can actually remove the embedded hypothesis. And the examples of the circle and Veronese support this conjecture. Okay, so I'm going to give what is the main ideas of the proof. So we have to exploit a lot the hypothesis of stability. So for that purpose, we need to find proper test sections. We have to define normal vector fields over our submanifold. So the proof is divided in 2 steps. The first one is if we know that the parameter tau is between the special value on 1 and our immersion is stable, then we derive that tau square must be the special value and the killing field psi has to be tangent to the submanifold. For that purpose, we consider test section coming from normal components of constant vector fields in the Euclidean, the complex space. Okay, this is because as tangent space, the tangent space to the Berger sphere is precisely the same as the tangent space of the standard sphere, and this can be considered as a linear subspace of a Euclidean space. These are precisely the same eigensections that are used by Simons to show his classic results. The second step is that now we know that tau square has this special value and also that psi is tangent to our submanifold. And we would like to show that in such case, the normal bundle to the submanifold is actually invariant by the complex structure J. In this case, we are going to use test sections coming from normal components of constant Hermitian matrices using the following schema. So we know that for tau less than 1, the Berger spheres are actually distant spheres in the complex projective space of dimension n plus 1. And complex projective space can be considered as isometrically embedded inside the space of Hermitian matrix, which is nothing but Euclidean space, using the well-known Tain embedding. So now if I consider a constant Hermitian matrix, I can decompose in normal and tangent component to the Berger sphere and then normal component to the complex projective space. This orthogonal component to the Berger sphere, or to our submanifold, is the one that we used as test section inside our index form to exploit the stability hypothesis. Well, the properties shown in step 1 and 2 characterize actually the immersion to be as a Hopf bundle. And we get the proof, we get the result. Now I'm going to present some consequences derived from the proof that can be seen as similar results to those of Simon's. So we consider a minimal immersion of a conform manifold M with psi tangent. Okay, then rho given by 1 over tau squared minus dimension plus 1 is actually an eigenvalue of the Jacobi operator. Okay, so whenever we consider immersion where the Killing field psi is tangent, we know that that particular value is always an eigenvalue of the Jacobi operator. Moreover, the multiplicity of this eigenvalue is precisely 2m, the codimension, 2m plus 1 minus d, and in such case, the immersion is actually a Berger sphere, totally geodesic Berger sphere of dimension 2m plus 1, or that multiplicity is bigger or equal than twice m plus 1. Okay. Moreover, if we restrict the parameter tau to the interval 1 over t plus 1 and less or equal than 1, where we already know that there are no compact minimal stable submanifolds, then the index of any submanifold with this property of having psi as a tangent vector field, this index is always less or equal than the codimension, and equality is attained if and only if the dimension is odd and n is congruent to a totally geodesic Berger sphere. And if m is not totally geodesic, so the index of the submanifold jumps to twice m plus 1. And finally, in the case of the orientally hypersurface case, so we've got that the index of m must be bigger or equal than 2n plus 3. As I have said, this is a similar result that the one of Simon's, but in the setting of the Berger sphere. So with this, we finished this 4 part and also the series of stability for minimal submanifolds. Thank you very much for following me until here, and again I would like to thank Jacobi for organizing this geometric analysis past, present and future online events, and also to Marcos Cavalcante and Jose Miguel Manzano for inviting me and give me the opportunity to give a talk here. So, bye.